All right, good afternoon, everyone. Are there any questions? No questions?
Is CodeCheck down?
No, CodeCheck should be up, I hope. But there may be some issue with the Git stuff. And so in that case, some of you email me some Git URL so that I can double check to see why that is the case. How are the other things now? Yes. Other questions? Yes.
What are your thoughts on quantum computing?
My thoughts on quantum.
Will we have to relearn everything soon?
I don't think soon, but you never know. But there'll be plenty of other stuff that you'll need to relearn. So, I mean, generally, you should expect that very few of the practical things that you learn in this class are going to survive 20 years. Like when you tell your grandchildren how you used to use Git, they're going to laugh at you. But the things that will stay as big O will still be around in 20 years. So the more conceptual things will certainly be there for a good long time. But yeah, I have no idea. Other questions? You have a question? Yes. Question 6 on the quiz. Which quiz is it? One, two, three, 4, 5. This one? This question? I can't tell which is question 6 from this here, so you have to tell me. So what's it say? Which operations from the list data structure could be used to implement the push and pop operations of a stack data structure? Okay, I need to draw a picture. So one of my options is remove first. So I guess remove first then would be pop. And then pushing happens at the same end as popping. So the answer would have to be remove first and add first, because add first adds at the same spot. And that's what it says. 2 and 3. Add first and remove first. What was difficult about it? Who asked the question? So, what's hard about it? What was confusing about it in your mind? See, add last would add here, right? And if you add, when you push and you pop right away, you're getting rid of what you just pushed. And if you were to add last here, then the popping would be here, and it wouldn't be the same thing. When you have a stack A, B, C, and now you push a D, and then when you pop it, the D goes right away. So a pop undoes the last push, and so they have to be at the same end. Other questions? Everyone is relieved about the easy homework and has no questions about the homework. Yes?
You have like pseudocode
You had a question about any old pseudocode or
It's how to approach 9C.
9C? All right, sure. Um, 9C final, right? We're past the draft. So let's see. So we have a bunch of words. And now I don't, I mean, one could compute the hash codes, right? But right now, just to make it easier on our mind, to develop some algorithm is, let's just assume that the hash code is their length. I know it's not, right? But let's just assume that this one here has hash code 4, this one has hash code 4, 3, 4, 4, 5. I'm just making this assumption. And so now what do we want to do? We're now reading in Fred, and we kind of need to remember it because we don't yet know whether there's going to be other words with the same hash code. Where do you want to remember it? So I'll make a table, and I'll put in Fred here. And then I'll see Mary, and I guess I should just remember her here. And then I see Tom, so I put another table entry. And then I see Paul, and Carl, and Henry. And so I'm building up this table. When I'm all done reading all the words, then I go through the table and I say, those ones that only had one entry, I don't care about those. And those ones that had more than one entry, I print them out. That's how I would do it by hand. So what is the table? What is the type of the table? Well, it's certainly a map, right? Anytime you have a table, it's a map. So, fine, it's a map. And what is the key type? So what is this type here? Integer. And what is the value type? So I heard some people say string, and sure, Tom is a string and Harry is a string. But what is this thing here? Is this a string? That's a set of strings, right? And so that's what it is. So that's the data structure that you have. It's a map where the keys are the hash codes and where the values are sets of the strings that have that as the hash code. As an aside, there's one minor technical ickiness. And I said it's a set of string because in the preceding lecture I said we should always use the interface type instead of saying hash set or tree set. But for nasty reasons that I don't want to get into, it does not happen to work in this circumstance. So over here, you actually have to put in either hash set or tree set. Which one do we want? Why? We want them later in sorted order, so we might as well just get them in this tree set. So you really have to put tree here. You know, on behalf of the clowns who messed this up, I would like to apologize, but one has to. So that's the data structure. So now we know how to do it by hand. So we're kind of ready to think, you know, how could one write this down in pseudocode? So I'm iterating through all of the words in a file, and I think that's something that at this point is a familiar operation. So I can say for each word W in the file. Well, actually, those of you who've done the pseudocode lab, a few of you have done it on Tuesday. Does anyone remember? It said, don't say the file. You should, in pseudocode, you should, you know, it's a good idea to give everything a variable name. So I'll call it in file. Or input, or whatever. So for each word W, and notice I'm giving the word W a name. That's always also a good idea. So now I need to put it somewhere, right? So I guess I need to have my map, and so I'll call it M. Now, in general, in pseudocode, we don't normally talk about types if the types are totally obvious. I guess here I have to break my rules and say it's not totally obvious. So I'll give the type, and I'll give the conceptual type. So for each of the words that I have, what's the first thing I want to do? So I read in the word, what's the next step? Get the hash code, totally, right? So H equals W dot hash code. And so keep in mind that pseudocode is not Shakespeare. So we're not saying allocate a variable h whose type shall be int and initialize it with what happens when you apply the hash code method on W, right? That would be somewhat wordy. And so we just write the shortest thing that gets us to where we want. So this is perfectly fine pseudocode. It doesn't have to be convoluted. All right, so now I need to do something. What do I want to do? I want to now add it to the bucket that has hash code H. So look at the case here. So I want to add it to this bucket. So can I just say that's not going to work at all, right? Because the bucket is not a word, the bucket is a set. So so I need to somehow fish that set out first. So fine. No, not H, M dot get. So here's my set. And now how do I get to add it to the set? So what I have in my hands right now for S is so I'm holding this set in my hands, and now I need to add the string to it. So how do I do that? I guess it's pseudocode. I could always say, oops, sorry. Right? Nothing wrong with it. That's 80% of the pseudocode for this problem. What's the remaining 20%? So every time that you deal with maps, What's special? The first time, right? The first time is special. So let's see what could be happening here the first time. So what if, and I'm going to leave that to you, but I'm going to write down the questions. What if m.getH is null? That means that there has never been a word with that hash code before. And maybe, what if S is empty? Is that a special case? So those are the things that you would want to think about, and then you want to patch up the pseudocode to deal with that case or those cases. And when you get that, you have an extra line or two of pseudocode, and then you're done. The rest will write itself. I guess I've also omitted the printing part, so let me add that here. So when you're all done, you print everything, and I'm not giving you the pseudocode for that right now. You'll have to figure that part out. Notice the device with the 3 dots. So I was thinking when I wrote up these rules for pseudocode, how to distinguish the precise parts of the pseudocode, the one that we know exactly how to do, from the nebulous parts that we're going to figure out later. So the convention that I put in the syntax rules is that it's okay to write the nebulous parts out, but then put 3 dots behind it to indicate, I know I need to do this, but I don't yet know how. And then as you refine the pseudocode, you can replace it with a function call or with a loop or whatever it needs later. So like when you post pseudocode on Piazza, and there's a part that you don't really want to worry about yet, you know it can be done, but that's not part of your question, use the 3 dots to say, yes, I know, I'm not giving you all the details here. But so when you look at this, it's beautiful pseudocode. Each line is either a simple statement or a loop that corresponds almost exactly to the loop in Java. And someone can read through this thing and can say, it's not going to work because. And right now the reason it's not going to work is, it's perfectly possible that S is empty, that S is null. And in that case, of course, you couldn't add something to null. Other questions? Yes?
So for my 9C final, I got it to work. However, I'm printing out the whole entire set, so it has like the brackets.
Yes?
Is that okay? But then I get rid of the brackets.
Does it pass the tester?
It passes the test. I just get rid of the brackets.
Get rid of the brackets. I'm surprised it passed the tester.
Okay.
I'll have to look at that. My intent was that I wanted you to iterate, because I wanted you to practice the iteration.
So I was wondering, because I got it to work because I got rid of the brackets, so it passed the test.
Yeah. Well, what I really was hoping that you would do is you would practice how to iterate through the elements of a map, and then how to iterate through the elements of a set. You don't have to use an iterator. You can probably well use a for loop, but I did want you to use the for loop.
Okay.
So I suppose you could call toString on it. But then what? I should have made it so that there's no commas. Okay, well, for next time, huh? Because if you remove all commas, that's obviously a bad strategy since there might be a comma in the word.
Okay.
Yeah. But so what I had in mind is that you do the iteration and do it. I mean, it's a useful skill.
Okay.
Other questions? Yes.
When you mean iteration, do you mean iterate through the set and then put it on a string and then print out the string?
Oh no, I didn't mean that. I meant that you make a loop. Let me.
Is that printed out on the string? Is that fine?
Like I say, it would be nice if you could. So what I had in mind is that you say, oh, I see. So the issue is then you have to do the commas, huh?
Yeah, I slap all the commas onto a string and all the elements.
Oh yeah, I guess you can do. I mean, you can do it. one way. Like I said, I want you to know how to do this iteration through the collections. Other questions? All right, looks like some of you have already gotten this finished, so maybe the homework is getting easier, or God forbid, you guys are getting better. Okay, so let's go through the lecture here. So there are these stacks, and so when I distinctly remember when I first learned about a stack, that it's a data structure where you can only access the top element, and you're not allowed to access any of the others. And all you can do is you can put something on the top, and you can remove it from the top. I said that's got to be the most pointless thing ever. Because if you have an array list, of course you can do all of those things, right? You can add something to the end, you can add something to the beginning, and so why bother about stacks? And so that's why I'm going to give you a whole bunch of examples later where one needs nothing but a stack to do some pretty interesting problems. So stacks by themselves are boring, but they have useful applications, and it's interesting to know that by doing nothing more than this, you can succeed. So queues. Another one of these data structures. Well, I guess with a queue, it seems it might be somewhat more useful, right? You could simulate a queue of customers in a supermarket. You have customers arriving at the end of the queue, and you have the cashiers dealing with the ones in the front of the queue, and so on. And that actually is a very real application where model the real world like that. But queues are generally useful anytime that you have more work than you want to do at some given time. Then an easy way of dealing with it is that as the work arrives, you put it in a queue, and then some other process, as that process has time to deal with them, they take them off a queue. That is super, super common in business computing and scientific computing everywhere. So queues are genuinely useful, and you saw that in one of the homework assignments. So when you think of this thing where we took some string and now we wanted to compute the permutations of that, and so then what did we do? We generated these other products, and then we said, oh, now we're too busy, and so now we put them at the end of the queue. So we took something out from the front of the queue, processed it, put results on the end of the queue, and we moved on. So that's a common way that queues work. The API is pretty simple. So there is to make a stack, you just make a stack, and it has methods called, with the traditional names, push and pop. So push pushes something on the stack, pop pops it off, and you get it back as the result. In some applications, you just want to look at the top of the stack without popping it off. Of course, you could pop it off and push it back on, but there's a convenience operation, peek, for that purpose. And the last and essential operation is to test whether the thing is empty, because if you pop an empty stack, that can't work. And so those are the fundamental operations. Now, the weird thing in Java is that there are other operations in java.util.stack. So let me show you that. So stack inherits from vector, and vector has operations such as get, and with get you can get any element in the stack. So in Java, if I absolutely wanted to look at this element here, I could. But you should never do that, of course. So if in an exam situation or in a homework you're asked to use a stack, you need to stay away from these unstack-like operations. So this was just a bit of a coding blunder that they were in a hurry, and it was 1995, they needed to get this thing out, and they just said, oh, we'll just inherit from vector, and yeah, so what if we inherit all of these methods? Surely no one is going to call them. So all you should use is these ones. Even search is weird. No one searches in a stack. So these people obviously didn't go to college. All right, so that's stacks, easy enough to use. And so you would never iterate over the elements in a stack. It doesn't make any sense. You can take them all off and then put them all back on, but that's really the only thing that you could do with a stack. Similarly with queues, so with queues, you only want to call add to the tail. And it's useful to remember the tail and head terminology, and you know what it's like, right? You stand there to pay your bills at the registration, and you enter the tail of the queue. And many hours later, you emerge from the head of the queue. So remove removes from the head. You can peek at the head, just like you can look at the top of the stack, and you can test whether a queue is empty to see whether it is legal to call remove or peek. So the names are slightly different, and these are just there for historical reasons, and they're perfectly good names. Now, the one thing that's funny about the queue is that in Java, there is no queue class. You will find a queue interface, here it is. And so the queue interface has the methods for adding and removing, and it also has a bunch of weird elements. There's a method called offer and poll. We're not using those. Those are meant for concurrent programming. Yes?
When you peek and you get the element and you say you alter it, then you table in the stack.
I'm sorry?
If I use peek and I get the element
Yeah?
and I mutate it, will you?
Oh yeah, don't do that. That's generally not considered. So as a general rule, when you have any old collection, you really need the basic assumption is that you don't mutate those things without knowing what you're doing. Like in a stack, you could say, it's still an ordered collection. I guess you could mutate it. But imagine you mutate something in a set. That would be very bad. So if you mutate something in a set and change it so that it no longer has the same equality test, you can seriously damage your data structure. So the basic assumption is that when you have something in one of these collections, you don't want to mutate them.
So when you pop it off.
You could pop, yeah, I mean the stack that rarely happens. But in a set, that really is a good example. You just want to structure your application so that the things that you collect are immutable. So generally I would say if I must mutate them for some reason, sure I could put them in an array list, that's fine. But these other data structures are just not suitable for that. So you can mutate, I mean specifically what you can't mutate is anything that is used to either the keys in a map or the elements of a set. You simply cannot mutate them. And you could with a stack, but it would be such a weird thing to do. All right, so what I wanted to say is that there's a queue interface, and it has the add and remove methods, and so that's what we're using here. Notice there was no stack interface. Stack was just a class, tossed in there in the early days of Java. Queue is an interface, has a few extra methods for concurrency that we don't care about, and as an implementing class, the go-to choice usually at this point is to just use a linked list. A linked list makes a perfectly good queue. You can add at one end and you can remove at the other end. It just works. Would an array list make a good queue? Do we have that as a question or no? So we're going to talk about that much more in a couple of weeks. But the short answer is no, because when you have an array list, it's easy enough to add to an array list, just adds at the end. But now let's say we want to remove, we would remove here, and what would happen? All these other elements would move down to fill the gap, and so that would be an O of n operation. And so you don't want to use an array list. For a queue, you want to use, a linked list is a perfectly good choice, and that's what we're going to be doing right now. All right, so priority queues, I'm not sure we're going to be doing anything useful with them right now, but it is often a useful data structure. So a priority queue is similar to a queue in a way in that you add things, but it's different in that when you remove, it removes the most important one and not the one who arrived earliest. So it's as if you were to queue up somewhere, and then the teller would always call out the most important person first instead of the one who had first arrived. Seems pretty unfair, but it's a useful data structure for other things, like when you need to organize work. You want to do the most important work first and not the one that happened to arrive there first. So there is a priority queue class, and if we use it, we'll come back to it. All right, so here is the first question that everyone has to ask about queues, and that is, and stacks, and that is, what does this crazy code print? So go and get out a sheet of paper and figure this out. Okay. 1, 2, 3, 4. Yes?
For the priority queue, how does it know which one's like the priority?
Oh, it goes by, the elements have to be comparable, and it goes, oddly enough, by the smallest value. So because if something is first priority, it's more important than something that's second priority. So it always takes the smallest one. Yeah?
When you're adding onto the priority queue, once you have 3 consistent elements, does it do the comparison for?
It doesn't quite do that. Let's see, you're not going to learn that until 146. It builds up an internal data structure that makes remove pretty cheap. So it semi-organizes them so that in such a way to lower the cost of remove.
Wait, sorry, I'm talking about after when it's adding.
Yeah, so what it does is it builds a tree structure, and the tree is organized in a clever way that will take me a bit long to explain. It organizes it somewhere, and it doesn't actually sort it. It could, of course, sort it, but that would be expensive if it resorted it every time. So it does a halfway thing where it puts it in a good location that remove gets cheap. But remove is not so cheap as to just take the first one. It's an interesting data structure. All right, so let's see. So S is stack. I push on 1. I push on 3. I push on 2. Right, so here's the top of my stack. Now what do? I pop and I add to the queue. So I add the 2 to the queue, and I'm leaving myself a little bit of room, so that now becomes the head of the queue. And then I put the 3 here and the 1 here, so the tail is here. And now I put them all onto a priority queue, where priority queue has no intrinsic ordering, so they are all put in here. So I already wasted my time figuring out what the ordering was. And now I pull them out of the priority queue. And the priority queue, of course, the first gives me the most important one, the one with priority 1, then the one with priority 2, and then the one with priority 3. And I could have figured that out without having done the preceding step. Did anyone do that and work backwards? All right, so let's see how everyone was doing. So again, so let me show you how to do it the easy way as it happens. The last one here was the priority queue. I know that the elements 1, 2, and 3 were sitting in there. It doesn't matter in which order. So we call remove. That removes the 1. We call remove. That removes the 2. We call remove. That removes the 3. And that's the answer. All right. Now some applications of these data structures. So in CS1, maybe you learned a simple trick to find out whether an expression such as this one here has balanced parentheses. Nowadays, of course, your text editor shows the balanced parentheses, right? And so when you mouse over one of the parentheses, or when you with cursors there, the other one is highlighted. But back in the days of punch cards, that wasn't the case. So when I was learning this stuff first, we learned a simple trick to find out whether the parentheses were balanced. And the trick went like this. You go over the expression. Each time you find an opening parenthesis, you add 1 to some counter that you keep in your mind. So I say 1, 2. And when you find a closing parenthesis, you subtract. I'm back at 1. I'm back at 0. I'm at 1. I'm at 0. And I'm at the end, so they're balanced. If you come to the end and the result is not 0, then obviously they didn't balance. But also, if anywhere in the middle you get a negative number, like let's say you had an extra parenthesis here and then an opening one here, overall they're balanced, but when you get to the point here, you get a -1, and that means the parentheses are not in balance. That is a perfectly good algorithm, and it doesn't need any stack or anything. But what if you have different kinds of parentheses? In middle school, sometimes your teachers think parentheses are confusing, and they introduce, these different kinds, like the curly braces, the brackets, and the parentheses. And now how do you test whether such an expression is well formed? That's where the stack comes in. So you push them on a stack. And so here's the algorithm. So you read the next token, where a token is a number or a parenthesis or a plus sign or something. If it's an opening parenthesis, you push it on a stack. So your stack has a bunch of opening parentheses on it. And now your next token is a closing parenthesis, so maybe you saw a closing parenthesis like this. If the stack was now empty, that would be bad. That means you had more closing than opening parentheses. You report an error. And if they don't match, then it would be an error. So if at this point you hadn't read in this one, but say a round parenthesis, then the round parenthesis would match the opening brace, and you would report an error. And otherwise, when you come to all the way at the end, the stack needs to be empty, and if so, the parentheses balanced. So here is a run through of this, and I'm not going to go through it. So let's try this. So run through this algorithm with these 3 inputs, and each of them is unhappy in a different way. So all properly balanced expressions are the same, but the wrong ones can be unhappy in different ways. And so here they are. And tell me which of the statements, and with 1, 2, 3, I mean the 1, 2, and 3 here, which of them fail for each of those? So, I'm just going to do the first one here. So we're pushing the left brace, we're pushing the left bracket, the parenthesis. Now we're seeing this parenthesis here, so we're popping this one off. We're seeing this bracket here, so we're pushing this bracket off. We're seeing another parenthesis, then we have a closing parenthesis here, so that pushes that. Now we see this brace here, so that goes. And now we're seeing this closing parenthesis, and the stack is empty. So let's see which one that was. That one was this case here. So we had 1. Sadly, that isn't good enough. So let's do the second one. So we have brace, brace, bracket, parenthesis, parenthesis goes, bracket goes, parenthesis, parenthesis goes, brace goes. So now we have a brace left over, and that is case 3, right? The stack is empty, is not empty at the end, so we would be returning false here. That should be enough to tell us that it was this one here. Let's see how everyone was doing. So people were kind of mixed here. Okay, so 31% are seriously confused here. More than that. So what's the confusion? Someone who's confused, ask a question.
Probably the difference between 1 and 2 for the return type.
Okay. Oh, you mean why this one says SDK is empty?
There's probably a mix up in how we understood when to return 1 versus 2, or 2 versus 3.
All right, so this one was, so we're reading a closing parenthesis, so we have some stuff on the stack, we don't know what. So we now looking at this closing parenthesis, and so if there was the wrong shape, then that's this case here. This part here only applies when we ran through the entire algorithm because it lines up with this while. So the empty test only happens at the very end. And maybe it's confusingly worded. You know, maybe you would have preferred if stack is empty, return true, else return false. Those two things mean the same thing. And, you know, I always prefer to write the more concise expression. But, you know, by all means, if you find the other one easier to read in your mind, turn it around like that. All right. Now, moving right on. So at some point in, I don't know, the Middle Ages, when people first started writing out math, you know, they started obviously with addition, and then multiplication entered the picture, and at some point someone had the idea to say that multiplication should be more important, and we write 3 plus 4 times 5, and we know that we first multiply the 4 and the 5. Why is multiplication more important? I mean, it seems completely arbitrary. Why doesn't this mean to do the plus first? Because the dot is smaller? I mean, you know, and actually, you know, what if you write it like this? It's just the same size. So what is the rationale for making multiplication? Why don't they just make it go left to right? You know, the earliest pocket calculators, that's how they worked. Everything was just left to right. You know, it's a mystery, right? So someone must have at one point decided multiplication, it's convenient to make multiplication more important. And so, of course, in many situations it is, because you might have like weighted averages where you have, or you know, simply quantities and prices. You have 3 things that are $29.95 and you have 4 things that are $39.95. And that kind of expression just happens to be more commonly than the other way around. And so someone at one point decided, we'll just make the arbitrary convention that multiplication is more important. And then, of course, we need parentheses to deal with the case when we want it the other way around. You know, when we want to have 2 times 29 plus 39, then we need the parentheses. But actually, there is a better way. So this Polish mathematician with this unpronounceable name has figured out a much better way of doing it. And so the way he does it is he writes the operator, like the plus, and then after them, he writes the 2 operands. So instead of writing 3 plus 4, he writes plus 3, 4. Now that doesn't sound like a big improvement, but it is, because now you don't need any parentheses at all. If I want to compute 3 plus 4 times 5, then I write it like that. If I wanted to compute 3 plus and then the 4 times 5, then I do the 4 times 5 and the plus 3, like that. So to you that probably looks weird, and that's because you're not Polish. So if he had come earlier, we would have all learned this in middle school, and we wouldn't have ever had to worry about parentheses, and it would become perfectly natural. You had a question? Yeah.
So how would you do double digits or more than one digit?
Oh, very good question. So if you wanted to add 3 numbers, let's say I wanted to add 2 and 3 and 4, I would say plus 2, 3, plus 4. Or if you prefer, plus 2, plus 3, 4. I'm sorry? Oh, that would be a space in between. So it would be plus, I mean, it doesn't show up very well here, 23. So they're not like keys on a keyboard. This guy invented it before the typewriter was invented. So now this sounds like something that no humans would ever actually learn, but that turns out not to be true. When the first calculators came out, there was one company, Hewlett-Packard in fact, who used this very same notation with a slight twist on their calculators, except that they made it so that the operators were backwards. So you would type 3, 4 plus, and to answer the question about what to do with the spaces, you actually hit 3 enter, 4 enter, and then plus. And that would enter the 3 in the calculator, would enter the 4, or you could, if you have multiple digits, you would 34 enter, 5 enter plus, 6 times. So you would write it out like that, and you would never have to use any parentheses. And so when I was at that age when these calculators came out, and I bought one of those, and it was great. I was so much faster than those yokels who had to type parentheses in there. And a few people still use them. You can still buy these calculators, and now, of course, they do have parentheses for people who don't want to learn this other way. But you can turn them into what's called this reverse Polish mode. And so some people still use it. And so you may want to try it, and maybe it's worth it, maybe it's not. But you notice that these calculators are different from a normal calculator in that there is no equal key. Because as soon as you hit an operator, the result is displayed. So when you type 3, 4, enter, 4, enter, or you can just say 4 plus. You don't even need to put this enter. You just say 3, enter, 4 plus, and then the result 3 plus 4 is displayed. And so these calculators were marketed as the calculators without equal. And they were, in fact, so much better than the competition. But it just didn't really catch on in a wide way. It is, interestingly enough, the same principle is used in the Java virtual machine. The virtual machine instructions operate on a stack in exactly the same way. Yes?
So, like, how would you do grouping? Like, where you square root of all these functions?
Oh, sure. So you would say 3, enter, 4 plus 5 times square root. And the square root is a unary operator that takes a square root of the top of the stack. So, instead of writing laboriously, what did it as? 3 plus 4 times 5. I'm not saying that any of you should learn this. I mean, it's obviously not a very useful skill, but people have done it. So, yeah.
So if it's something like 3, 4 division, would it be 3 by 4 or 4 by 3?
Very good question. So 3, 4 division or 3, 4 minus. This would be 3 over 4. And this would be minus 1. So the second operand is on the top of the stack and the first operand is below that. So there is an algorithm, of course using a stack, to compute this, and it's very simple. Whenever you see a new number, you push it on the stack, And whenever you see an operand, you pop off the arguments. So if you have like 3, 4 plus 5 star, then you push the 3 on the stack. You push the 4 on the stack, so I should make the top right. So here's the top. Then you see the plus, so you pop these things off and push the result on the stack. Then we have a 5 here, you push that on the stack. And the times means you pop off the 2 and you multiply and push the result. That's the algorithm that's used inside these calculators. And that is also the algorithm that's used inside a virtual machine that does these things. So let's see how good you are at this. So imagine you had a Hewlett-Packard calculator. What would you get out of this? So let's see. So we push 2, we push 1, we push 3, and now we add. So 1 plus 3 is 4. Now we multiply. 2 times 4 is 8. We push 4, and we subtract. Okay, let's see if we can't get a few more here. So when we subtract, do we subtract 8 minus 4 or 4 minus 8? So it says over here in the algorithm, it says arg2 is pop, so arg2 is the 4. It says arg1 is the next pop, so that's the 8. And now it is apply the operand, which is minus, to arg1 and arg2. So presumably that means to compute 8 minus 4. And then the answer would be 4. And so that is the majority answer. That was so this one here was minus 4. And I mean, that's a plausible misunderstanding because of the order. I mean, none of the above is a plausible answer because, what if you just made a computational error? I'm not really sure how you could have gotten to 7. So those 10 users who got 7, just don't answer these things randomly. All right, in the interest of time, I'm going to skip this question here. Now, how do you write this expression in reverse Polish? There's obviously a way to do this. But I'm going to show you a more interesting algorithm that also involves stacks. And that has to do with the much more common question, what if you have a regular old number, expression, 3 plus 4 times 7 minus 2 divided by 8 or some such thing. And you have it in text as a string, and now you want to evaluate it. Of course, there's an easy way to evaluate it, right? You can form a string that says public class test public static void main string bracket args system out println, inject the string in there, pass it to the compiler, and then capture the printout, right? But that seems like a bit overkill. And anyway, somehow the compiler has to be able to deal with these expressions. So it's useful to know how to do this. So the algorithm that lets you do that uses two stacks. One stack for the numbers, one stack for the operators. And so I'll give you a simple example here. Here we're evaluating the input 3 plus 4. We're reading the first token and putting it on the number stack. We're looking at this token here that goes on the operator stack. Here it is. We're reading the next input 4, and we're putting it on the number stack. Now we have no more input, and now we start evaluating what we can. And so what can we do? We pop this operator off, we pop the two operands off, and we put the answer on the stack. So that's how we would do something like 3 plus 4. Let's do a more complicated one. Here we have 3 times 4 plus 5. So the first token gets put on the number stack here. The star here gets now exposed. That's our next token. It goes on the operator stack here. Then the next number here goes on the number stack. Now we have a plus here that gets exposed. And now something interesting happens. Because the plus is weaker than the star, we want the star to happen first, we don't push the plus. Instead, we compute what's already there, namely 4 times 3, and push the result on the stack. And only afterwards do we put the plus on the operator stack. So we never want to put a weaker operator on top of a stronger operator. Instead, we evaluate the stronger operator and only then put the weaker operator on. And so now the rest is routine. We put the 5 here on, we have this operator, and now we're at the end of the input, so we clear out everything and say 5 and 12 and 17. So that's the algorithm that deals with precedence. How about parentheses? So in this case here, we see the 3, put it on the stack. We see the star, put it on the operator stack. We see an opening parenthesis, and we put the opening parenthesis on the operator stack as well. And now, when the plus comes along, the opening parenthesis is on the top of the stack, and it hides the big, bad, strong star. And so that's why we now keep on pushing the plus. And so that gets the plus to be executed first. So now we push the 5. When we find the closing parenthesis, then we pop up everything until the opening parenthesis is exposed. So that in a nutshell is an algorithm. Nice algorithm to know if you ever have to do this kind of stuff. But I'm not going to go through the details right now. Does anyone remember we previously had a different way of computing this kind of expressions? Where did we do that? In which lecture? It was in recursion, and what was the topic? Mutual recursion, thank you, yes. So we previously had an algorithm with these 3 functions, expression, term, and factor, that mutually called each other, and everyone thought that was the clearest and most intuitive thing ever. And so here you have another example where by using a stack, you can bypass the recursion. So in the recursion, these things were implicitly put on a stack, on the runtime stack, and here we're making the stacks explicit. So That's an algorithm. All I want you to know is that such an algorithm exists. The more interesting use of stacks is if you is for backtracking algorithms. So let's say you want to escape a maze here, and so you're here, this green creature here, and you can go in various directions. You could go up or left or down or right. On a stack, you put the various places on how you can go. So here we're saying I am at 3, 4, and I could be going, as it happens in this case, in all 4 directions. So that's what you do. Now you've done that preparatory step, and now you pop off the top thing of the stack, that is the 3, 4, and you actually do it. You go northwards, the 3, 4 until you can't move anymore. Now you do it again. In this case, there's only 2 moves you can do. You can go 1, 4 to the right, and you can go to the left. And that's what you do. You push these things on the stack. Now, time for action again. We pop off the top, which is 1, 4 to the right, and then that gets us into this corner here. At this point here, we can't do anything anymore. There's no other direction that we can go instead of the one that we just came from. So in that case, you now pop off the top of the stack, you return to where that thing was, which is the 1, 4, and then you move along. In this case here, that means now we can go to the left. Well, then the same thing will happen again. So if you follow this thing through, the stack keeps all of the possibilities that had been previously unexamined. So at each point, you can make a number of decisions. You push them all on the stack. You pop off the top one and you follow it. And then you keep on going and more stuff ends up on the stack. Eventually, none of the decisions that you made may have proven successful, and you get them all cleared out eventually, and you come back to this point where you say, gosh, I could have done these 3 other things, and you pop off one of them, and you try that one. So the stack organizes all of the different ways in which you can try this. This is one of those things that, you're not going to get it by me talking about. You're going to have to try that at some point on your own and see how that works. But it's plausible that a stack can keep track of all of these decisions that have yet been taken. So here's the algorithm. And in the last 6 or 7 minutes, we're going to put this to use in a different case, not with maze escapes, but with another point where we had to make decisions. So recursion here, so you remember that I made you use recursion to do this number puzzle thing, where you had to solve these puzzles. Where each of the letters corresponded to some digit. And so there was a recursive way of solving that. I don't know if there's a solution to this particular puzzle. There was a recursive one where I don't even remember how it goes, but you'll remember. So here's my non-recursive way of doing it. So we're having a puzzle that right now has all letters, or maybe some letters and some digits already. We're adding it to a queue. So for whatever reason, I'll do it with a queue right now instead of a stack. I could have used a stack. While the queue is not empty, I remove the first one that hasn't yet been solved. Or maybe it has been solved. So I'll double check. If it's solved, then I'm done. But if it's not solved, I will take its first letter. So let's say that this one was 17b plus 7bx equals 3b4. Well, that can't happen, right? 1, 3b4. Can't happen either, but whatever. And so now what's my first letter? This would be my first letter. And now I put in all of the digits that I don't yet have, and I'll get new puzzles out of this, such as 172 plus 72x equals 1324. And 17, can I use 3? No. 175 plus 75x equals 1354. So I get a handful of these puzzles. I put them all back in the end of the queue. That's all I'm doing. No recursion, no nothing. I just pop one off the front of the queue, try to do it a little bit better, put it back to the end of the queue. So now go ahead and do that in CodeCheck. So here's the solution from the homework, the recursive one. And now we're going to do it with the queue. So here, now go ahead and do it right now and start working along with it. Oh, how do you make a new queue? You can't say new queue. New linked list, yeah. Okay, so now so we take the newest one from the queue. How do you get one out of the queue? Yeah?
So if we chose between recursion and list, stack list, will we always choose the stack list?
No, you always, recursion is actually easier.
Isn't the list faster though?
No, it doesn't, I mean, the difference in speed is negligible. Because either way, if you use recursion, there is a hidden stack, there's a runtime stack. So I wouldn't worry about, there's some problems where it matters, but they're few and far between. So I would always use what is the easiest way of understanding it. And the queues are not actually unintuitive if you think about, I'm also kind of lazy. I grab something off the front of the queue, I simplify it just a little bit, and I toss it back at the end of the queue. It's a different form of laziness. With recursion, I say, oh, I assume someone else knows the answer, and I'll let that someone else do the partial answers and then I merge them together. I prefer recursion because I'm so much happier when someone else does the work. With the queue, I put it at the end of the queue, and it means I still have to do the work, and recursion signals to me that someone else. But it's one or the other. So I like the idea that you see the same algorithm in both ways. All right, so we remove the queue here, the puzzle. And now if it's not solved, over here, previously, we solved the puzzle. And so that's what we're not supposed to do here. So we're not supposed to call this recursively, but instead, I'm supposed to do this thing here and just toss it back to the end of the queue. Let's see, is that all? I guess I must have missed a parenthesis. Aww. How do you test whether a queue is empty? I guess, yeah. It is empty? Okay, well, how about this? Okay, CodeCheck hates us. Here. Okay, so here it gave us the solution here. And now if I could have 30 seconds of your attention because I have one super important question. What would happen if you replaced the queue with a stack? So, is that a crazy thing to do? Will it not work at all? Or will it work? What do you think? it'll actually give you the results in reverse order. So it'll perfectly well work. A stack is just another way of organizing your work. So the question is, when you are just done with something, so you grab something, you improve it a little bit, and then the question is, do you want to work on it more, so you put it on the stack, or do you want to leave it undone for as long as possible, then you put it in a queue. All right, that's all. I will see you in a week.